Continuous random variables. Probability distributions are of two types. One is discrete and other is continuous probability distribution. The random discrete variable used to define the discrete distribution is called discrete random variable. And for a continuous probability distribution, we use the continuous random variable. So let us try to understand what a continuous random variable is. Let's consider the example. All of us have ordered a pizza at some times in our life. So consider yourself as a manager at one of the pizza delivery outlets. Now, as a delivery manager, you are concerned with the average time it takes for a pizza delivery to reach a customer. So let's consider a random variable, which is the exact amount of time required for a pizza delivery to reach a customer. Let us name this capital X. And let's say that this X is calculated in minutes. Now let us list down all the possible outcomes of this random variable. It could be 5 minutes, which means that the customer was probably in the neighboring building, or it could be 30 minutes. It could also be something like 15.13473 minutes. You can even think up to the last millisecond or up to the last microsecond level. Even 15.13473 might not represent the exact amount of time, because we could go up to 100 of decimal points, right? So technically it could be a whole number like 15, but it could also be a decimal and could go on till infinite decimal points. So when you use words like exact amount of time, or say the amount of water present in a bottle, or exact stock price at the end of a trading session, or anything that is generally exact, this is always going to be a continuous random variable. And the reason is that the moment you say exact, the values that the random variable can take is going to be infinite. Even just between 20 and 20.1, there could be a million values. Whenever you have such kind of random variables, they are called continuous random variables. So to understand how we actually represent a continuous random variable on a graph, so let's create a plot with x-axis as the outcomes of the random variable. Now, in case of a discrete random variable, remember that the y-axis used to represent the probability value for that specific value of x, and the plot would look very similar to a histogram plot. But in the case of a continuous random variable, that is not possible. This is because you cannot define the probability for any specific value of x, and it will be too small, almost close to 0. So typically how you represent a continuous random variable on a graph, as the name suggests, it will have a continuous line. And this graph is known as the probability density function. Now in the case of a discrete random variable, we used to calculate the probability by saying probability of x equal to 0 or probability of x equal to 1. Or we would simply plot these values on the plot. Now think in the case of continuous random variables. If I go back to the example of commute time to a customer and ask you what is the probability that x will be exactly 15 minutes, since the possible outcomes that x can take is almost infinite, so the probability that x will be exactly 15 will be almost 0. And this is true for any value of x. Therefore, we can say that the probability of x being any specific value is always 0. So instead what we do, we measure the probability of x lying in a certain interval. Let's take an interval from 20 to 30 minutes. The way we'll find this probability from the graph is that it will be the area under the curve between 20 and 30 minutes. So the area that has been colored in the plot is the probability that x lies between 20 to 30. Now let's assume that the maximum time is always 1 hour, and any time above that is not considered in our data, as that scenario is extremely rare. Then the commute time can range anywhere from 0 to 60 minutes. Thus, a random variable x will also be a line that will range from 0 to 60 minutes, and total area under the curve from 0 to 60 will be 1, which is the maximum probability of x. So we'll conclude this discussion by quickly going over the points that we have learned. First, a continuous random variable can have infinite number of outcomes. Second, we represent a continuous random variable using what we call a probability density function, which is essentially a continuous line drawn for all the range of values that x can take. Thirdly, the area under the curve represents the probability that the random variable lies in that interval. And finally, the total area under the curve will always be equal to 1. Continuous probability distributions. Cumulative probability for continuous random variables. Let us understand the concept of cumulative probability for a continuous random variable. So let us take an example where we have considered some probability density function. So we have x and y axis. So this is our continuous random variable. Let it be defined by capital X. The x-axis goes from plus infinity to minus infinity. On this chart, we have also marked -1 and +1 for x random variable. And if we have learned that we want to calculate probability of between x between 1 to -1, then that will be the area under the curve from -1 to +1. Let us understand what will be the cumulative probability for this graph. Suppose we want to find the cumulative probability of x equal to -1. What it signifies is that it's going to be the area from minus infinity to minus 1. Though in this case, it does not go till minus infinity, but basically till whatever point it goes. So this region is the cumulative probability of x equal to minus 1, that is from minus infinity to minus 1. The same concept can be applied to find the cumulative probability at x equal to 1, and that would be denoted by the shaded region from minus infinity to plus 1, basically all the values from minus infinity to plus 1. Now the cumulative probability becomes very important when we talk about continuous random variables, because in such cases we are always dealing with ranges. So let's say you are given the cumulative probability for x equal to 1 and x equal to minus 1 as 0.6 and 0.5 respectively. So using these values, can we find the probability of x lying from minus 1 to plus 1? We can say that the probability of x between minus 1 to plus 1 is nothing but probability of x less than equal to 1 minus probability of x less than equal to minus 1. And this value can give us the area under the curve from minus 1 to plus 1. So in this case, probability of x less than 1 is 0.6 and probability of x less than minus 1 is 0.5. So the probability of x lying between plus 1 to minus 1 is 0.1. Continuous probability distributions. Normal distribution. The normal distribution is perhaps the most widely used and most important distribution when talking about distributions of continuous random variables. And there are a few valid reasons why this is the case. There are many places where the normal distribution appears naturally. For example, if you take the height of an individual in a country, it will most likely follow a normal distribution. Therefore, the normal distribution approximates a lot of real-life data. The second reason is that once we know that something follows a normal distribution, and knowing that normal distributions have some interesting properties, it makes it very convenient to work with them. And the third reason is that the normal distribution appears in a very important theorem which will form the base of most of the inferential statistics problems that we'll solve. This theorem is called the central limit theorem. For these reasons, the normal distribution is an extremely important distribution. So to understand the normal distribution, let us go back to our earlier example of commute time for pizza delivering to the customers' houses. We are aware that pizza delivery outlets have come up with this 30-minute guarantee of delivering pizza from the time an order is placed. If the time taken to deliver the pizza is more than 30 minutes, then depending on the purchase value, the pizza comes free or with a huge discount on total purchase. As a manager at one of the pizza outlets and given this 30-minute guarantee, you want to ensure that most of the pizzas are delivered well before these 30 minutes. For now, let's consider only those commutes from the pizza outlet to the customer's location and not include the deliveries where the delivery boy has to visit multiple locations as he is delivering multiple orders. So assume that it takes a maximum of 10 minutes to make the pizza. That leaves us with only 20 minutes to deliver the pizza from the outlet to the customer's location. The commute time would obviously vary from one location to another. For one customer, the commute time could be 10 minutes, while for another customer, the commute time could be just 5 minutes. While for yet another customer, the commute time could go up to 15 to 20 minutes. How do you think the probability density function for such a scenario might turn out? When we plotted the graph, we got a bell-shaped curve that looks like this, as shown here. This chart is known as normal distribution. Let's try to understand this chart. You can see that the probability density is highest at 10 minutes. This shows that the average commute time is 10 minutes, and in most cases, commute time will be close to 10 minutes. Obviously, it may not be exactly 10 minutes. It might be a value like 10.002 minutes, but we shall ignore this difference for now. We can also see that the probability density starts decreasing as we move towards right or left. Such a plot is known as normal distribution. Just by looking at this distribution, we can take several observations about the characteristics of this distribution. First, the mean of this distribution, which is in our case 10 minutes, lies in the exact center of this distribution, and this distribution is symmetric around its mean. Second, since the distribution is symmetric around the mean, which is 10 minutes, it means that 50% of the values are less than the mean and 50% are greater than the mean. This kind of a shape is called a bell curve, as it looks like the shape of a bell. Third, we can see that the probability density is highest at the mean and decreases exponentially as we move further away from the mean. In simple language, it means that there is a high probability that the value of the random variable is close to the mean. As we move further away from the mean, the probability of the occurrence of such values decreases. In our commute example, this would mean that the probability of the time being around 15 minutes is much lower as compared to the probability of the commute time being around 10 minutes. but it would still be higher compared to the probability of the commute time being around 20 minutes. Similarly, if we go below 10 minutes, then the probability density again starts to reduce and we would get a plot similar to the one shown here. So this is how you identify a normal distribution. Such distributions are very common in nature, be it heights and weights of people, amounts of rainfall, and many other places. Let us now generalize any normal distribution using some parameters. Any normal distribution can be defined using only two parameters, mean mu and standard deviation sigma. The mean, which is mu, is located at the center of normal distribution, and that point also denotes the median and the mode of distribution. In our case, the mean was 10 minutes, but in general it can be any value. Depending upon the application, the mean could be positive, negative, or 0. Here you can see how the distribution changes as we are changing the mean from -10 to 0 to 20. The second important parameter to distinguish between two normal distributions is the standard deviation, which we have denoted by sigma. For example, if I flatten the curve, you can see in the figure, and this shows that the standard deviation has increased. Similarly, if you try to narrow the same curve, it shows that the standard deviation is decreasing. Probabilities for a normal distribution. Suppose we have a normal distribution graph here, and let's say that the mean of this distribution is mu. We'll assume that its standard deviation is given by sigma. Now, very important rule that will keep coming as we will see the normal distribution is the empirical rule. This is nothing but some standard probability values that we can easily calculate for any normal distribution. So again, we have a random variable x, and we know that x follows a normal distribution with mean mu and standard deviation sigma. The empirical rule states that the probability of x lying between mu minus sigma and mu plus sigma is around 68% or 0.68. The probability of x lying between mu minus 2 sigma and mu plus 2 sigma is around 95% or 0.95. And the probability of x lying between mu minus 3 sigma and mu plus 3 sigma is around 99.7% or 0.997. This is a very important concept in a normal distribution. Let's go back to the pizza delivery example where we need to deliver pizzas to various customers who live in different parts of the city, and hence the delivery boys have different commute times. Now the commute times of each of these deliveries were measured, and it was found that the commute time follows a normal distribution with the average time of 12 minutes and a standard deviation of 3 minutes. So what information do we have about our distribution? We know that the mean of the normal distribution is 12 minutes, which is our mean, and the standard deviation is 3 minutes, which is our sigma. Suppose we want to know the probability of any delivery taking about 6 to 18 minutes to reach a customer location. If we plot this on normal distribution, we know the value mu is given to us as 12 minutes. And if we see on the left symmetry and right symmetry, we know that the standard deviation is 3 minutes. So mu plus 1 standard deviation will be 15 and mu plus 2 standard deviation will be 18 and so on. Similarly, on the left hand side, mu minus 1 standard deviation will be 9 and mu minus 2 standard deviations will be 6. Again, because our mu is 12 and standard deviation is 3. Now, as we have seen our 1, 2, 3 rule, we want to know the probability of the commute time x lying between 6 and 18 minutes. Since we know mu and sigma, we can write 6 as mu minus 2 sigma, which is nothing but 12 minus 2 times 3, and we can write 18 as mu plus 2 sigma, which is basically 12 plus 2 times 3, and using the empirical rule, we know that 95% of the population lies between mu minus 2 sigma and mu plus 2 sigma. Or in other words, 95% of the deliveries are actually taking 6 to 18 minutes to reach the customer location. Now, let's say we want to know the probability that the delivery time is between 6 and 21 minutes. So number 6 can again be written as mu minus 2 sigma because mu is 12 and sigma is 3. And now we can write 21 as mu plus 3 sigma. Similarly, if you see the right symmetry of the normal distribution plot, you can see that the area under mu to mu plus 3 sigma is at 49.85% of the population. Why 49.85%? Because we know already that the area from mu minus 3 sigma to mu plus 3 sigma is 99.7%, and therefore we are just simply taking half of that. So on the right side of the curve, we'll say that the area under the curve is 49.85%, and on the left side of the curve, we see that the area will be half of 95%, which is 47.5% of the population. So upon adding these two, we get 97.35% of people. This means that 97.35% of the pizza deliveries actually take 6 to 21 minutes as commute time to reach the customer locations. On similar lines, suppose we ask what is probability that x is less than 15, or in other words, the percentage of pizza deliveries where the delivery boy is taking less than 15 minutes to commute to the customer location, then it will be probability of x less than mu plus 1 sigma. Now let's try to calculate this value. We can divide this area into two parts. one below 12 minutes, which is going to be 50% because 12 is the mean of the distribution and it is on the center. And the second region will be the probability that x lies from mu to mu plus 1 sigma. And this value will be half of x lying within one standard deviation of the mean, which was 68%. Hence, the probability that x lies between 12 and 15 minutes will be half of 68%, which is 34%. Now, when we add these two areas, we get 50% plus 34%, which comes out to 84%. Thus, we can say that 84% of the pizza deliveries are actually taking less than 15 minutes of commute time. Standard normal distribution. In previous example, we had seen that our mean commute time was 12 minutes and our standard deviation was 3 minutes. And we tried to find the percentage of pizza deliveries where the commute time is between 6 and 18 minutes or 6 to 12 minutes. In those cases, we were trying to find the commute time which was exactly falling within mu plus some fixed number of standard deviations, and it could be 1 standard deviation or minus 1 standard deviation. But suppose you want to find what is the percentage of deliveries where the commute time is between 6 and 17 minutes or between 6 and 16.95 minutes. In those cases, we'll need some other techniques, for example, the standard normal distribution. Let us go back to our normal distribution of the commute time. Here you can see that we have our mean as 12 and standard deviation as 3. Earlier we were considering x to be values like 15, 18 and 21, which were multiples of 3, so that we could represent them as mu plus 1 sigma, mu plus 2 sigma and mu plus 3 sigma respectively. But what if I consider a value like 17? Here we can see that mu is 12 and x is 17, and the difference between these two values should be 5. So if we have to represent x in the form of mu plus some other multiples of sigma, then we can find this multiplication factor by using x minus mu divided by sigma. For instance, in our case, x minus mu upon sigma comes out to be 17 minus 12 upon 3, which equates to 5 by 3, which is equal to around 1.67. We can now represent 17 as mu plus 1.67 sigma, and we can use some technique to estimate the probability. The value x minus mu upon sigma is denoted by z, and z is called the standard normal variable. So essentially we always convert our x into some form of mu plus z times sigma. If we want to calculate the probability of x lying between mu minus 2 sigma to mu plus 2 sigma, it is the same as finding the probability that a new random variable z, which we mentioned earlier, was called the standard normal variable and lies between minus 2 to plus 2. Thus the probability of z lying between minus 2 to plus 2 will be 95% as per the empirical rule. Similarly, the probability of x lying between mu minus 1 sigma and mu plus 1 sigma is the same as the probability of z lying between minus 1 and plus 1, which is 68%. And finally, the probability of x lying between mu minus 3 sigma and mu plus 3 sigma is the same as the probability of z lying between minus 3 plus 3, which is 99.7%. Whenever we have some random variable x and we want to find the probability of x within a certain range, we can calculate a new random variable by finding out x minus mu upon sigma, which is z, and we can now say that z will follow the standard normal distribution. Let us see the difference between normal distribution and the standard normal distribution. If you see the normal distribution, you have a mu, like in our case mu was 12 minutes, and on the right side you can see that we have marked mu plus 1 sigma, mu plus 2 sigma and mu plus 3 sigma. Similarly, on the left side you have mu minus 1 sigma, mu minus 2 sigma and mu minus 3 sigma. And this we have seen with the empirical rule in the previous discussion. If you see the standard normal distribution, then our mean is always 0 and the standard deviation is always 1, and mu plus 1 sigma will be 1, mu plus 2 sigma will be 2, and on the left side you will have mu minus 1 sigma marked as minus 1 and so on. So that is the difference between our normal distribution, which we marked by x, and the standard normal distribution, which we marked by z. We'll now look at an example problem on standard normal distribution. How do we proceed to solve the problem of calculating the probability that an employee will take less than 17 minutes to compute to the office? So let's first convert this to the standard normal distribution and then see how we can calculate the probability from here. First, let us convert 17 into the z value. Remember that the mu and sigma for this distribution are 12 and 3 minutes respectively. Thus, calculating x minus mu upon sigma, we get 17 minus 12 upon 3, which equates 5 by 3, which is 1.67. Thus, probability that x is less than 17 is the same as the probability t z less than 1.67. So how can you find out the probability of z equal to 1.67? If you observe carefully, we are essentially calculating the cumulative probability for z equal to 1.67. Fortunately, some mathematicians have calculated all the probabilities and put them in a table which is called z table. This table gives the cumulative probability for a value of z, And let us see how you can find this Z table to find the cumulative probability at Z equal to 1.67. For doing that, we'll see the row based on before and after the decimal. So this value 1.67 can be broken into 1.6 and 0.07. Next, we'll search for the row corresponding to 1.6. As you can see that we are there, and we can see the second decimal place in the column. So we'll select the column marked as 0.07. So at the intersection of this row and column, you can find the cumulative probability of Z being 1.67, which is 0.9525. This kind of calculation can be easily done from Z table, Excel, and various other programs like R and Python. Thus, we now have the probability of Z less than 1.67, or the pizza delivery commute time, which is less than 17 minutes, which is approximately 95.25%. In Excel, this can be found using the function 1 minus norm.dist bracket minus 1.67, 0, 1, true, or we can also use Z table for here. In this lesson, we understood the concept of probabilistic events and sample space. We also examined the probabilities of intersection and union of events when two or more events are combined. We also discussed the computation of conditional probabilities with the help of Bayes' theorem. We examined the computation of joint and marginal probabilities. Next, we introduced random variables and probability distributions. We also computed the expectations and variance of a random variable with a given probability distribution. Two key distributions which we focused in detail included binomial and normal probability distributions. For these distributions, we examined key properties such as expected value, standard deviation, and cumulative probabilities. For more advanced discussions, our focus remained on continuous random variables and normal distributions, given their integral role in applications such as central limit theorem, confidence interval estimation, and hypothesis testing. We also examine a very important version of normal distribution, that is standard normal distribution. These discussions will act as building blocks to more advanced applications in statistical inference and predictive analytics. In the next lesson, we'll discuss descriptive statistics.